All right, welcome to today's CMOS lecture, CMOS MEMS lecture. It's going to be a warm day, but not as warm as yesterday. I feel much more comfortable today than yesterday, honestly. Yeah. So I hope that we'll have a pleasant time for the next 1.5 hours on some remaining topics of stress sensors. And the first topic is about a robust high pressure sensor that was developed by one of my PhD students some time ago on the basis of an idea that came from the University of Mannheim. Yeah? The top structure is was kind of the original structure of Professor Vertschützky and his collaborator, and it was designed to measure high pressures. And by high pressures, I mean, when one talks about high pressure, one means several hundred bar up to thousands of bar. I mean, 1 bar is known to everyone. It's the atmospheric pressure. Nobody knows how much it is because we don't really feel it. But when you go down 10 meters in water, you have an additional bar, and you feel that in your ears. Yeah, if you don't do anything against it. Yeah, it's a strong pressure that causes pain. Yeah, and now you imagine 2,000 bar. What causes 2,000 bar? Well, the combustion engines at the moment of explosion, of course, create a lot of overpressure, and that amounts to this range of pressures up to 2,000 bars. And so companies who want to do control of engines by, you know, selecting the right moment, when to inject, when to start the spark to let the gas mixture explode. Those need to know, you know, what the state of the engine is, and the pressure curve is one piece of information of that. And so sensors that can measure these high pressures are not so easy to build because 2,000 bar is a lot. If you want a pressure vessel that supports 2,000 bars, it's not so easy. You need a strong engine. That's why there is so much metal in these engines, so they don't fly around your ears. And so what is the idea of this pressure sensor? It's essentially a bimorph. Yeah, a bimorph consists of 2 materials with different mechanical properties. Usually bimorphs are thermal structures that combine 2 metals, bimetals. You have certainly heard that. That have different expansion coefficient under temperature change. And so when the temperature changes, there is some bending induced. And then maybe, you know, at some point of temperature, a contact is interrupted and then it doesn't heat anymore or something, you know, some process that requires a current to flow or not to flow can be controlled. But here it's more about the mechanical properties. We have a glass layer and we have a silicon layer. They have different elastic properties. So under pressure, they will contract differently. They will be compressed differently. And you can imagine that if hydrostatic pressure, that is isotropic pressure from all sides, is exerted on this structure, then the glass that is softer in the sense of more elastic, will compress more, while the silicon will resist that compression more, and there will be a bending induced. This whole structure will be led into a bending deformation. And then the idea of that original work was to implement some piezoresistors on the surface to note that bending. And with the knowledge that we have now, probably we'll say it's amazing that the resistors are so much in the center. If they were totally in the center, because of the symmetry of the structure, of course, the stress in the center is isotropic. Sigma xx, under this bending is the same as the bending in the y direction as sigma yy. And the action of the Poisson's ratio would be the same, also under 90-degree rotation. So there will be isotropic stress. Sigma xx is equal to sigma yy. And if you do now an implementation of the Wheatstone ridge right at the center, you can be sure to get no signal out. Because what matters is the difference sigma xx minus sigma yy. at these different locations. And so obviously they did not put the resistors right in the middle all at the same time, but they, for geometrical reason, had to put them somewhere else, and maybe they also optimized that a little bit, and so they got a signal out. But it was not as strong. And Mark Baumann, who is now project leader at TDK Micronas, I thought, okay, I can do better. First of all, I can adapt this ratio of materials to optimize the sensitivity. Maybe if I put more glass below, then I can reach a stronger response up here. And then also to create this anisotropy of stress, let me do some micromachining. And we implemented these surface trenches into the silicon to let the material expand in one direction, whereas it is still constrained in the other direction. You can think of this internal structure here as like a beam that is clamped on both sides, and it cannot expand in the longitudinal direction apart from what the motion that is imposed to it, but it can freely expand laterally. So you will create an asymmetry. X and Y, or here in this direction, X prime and Y prime are not equivalent in this central position. So one can expect a better response. And indeed, with some optimized dimensions, he obtained a sensitivity that was 67%, no, what do I say? 6.7 times larger than in this original structure, and also for a device that was smaller. So about 1 cubic millimeter. So it's a really small piece of material, sensor dust. And just to show you how this works, I'll show you a little animation that I only have in PowerPoint. So here it is, I think. Let's see if that works. That same picture. If I click on this, now you see the effect of pressure acting on that structure. And what you see is that the glass body below tries to compress more. At least at the bottom, you see how much it is compressed by this isotropic pressure. And we're talking about, some small. Now that's only a numerical applied pressure. So 0.1 megapascal is 1 atmosphere. So this is only for the effect of showing. And then you can multiply it by a factor of 20,000 to know what happens under 2,000 bar. So again, if I click on it, what else will you see? You see that the silicon doesn't follow so much. The silicon is indeed bent. And then on the top surface of the silicon, you see some stress that is occurring. So 0 is green, and then blue is negative, and which stress is being meant? It's the stress sigma xy. So it's not the longitudinal stress in x direction or the longitudinal stress in y direction or the difference sigma xx minus sigma yy, but it's sigma xy, the shear stress, which corresponds, of course. Is that the PowerPoint? Yes. No, that's the, so the, here we have our x prime direction, and this is the y prime direction, and sigma x y is equal to sigma x prime minus sigma y prime. So the longitudinal stress in this direction, and then whatever stress in the other direction, yy, may be different, and that difference causes the response of that piezoresistive sensor implemented right in the middle, and it's equal to sigma xy in the original coordinate system aligned with the axis of the structure. So this is also shown here. You see here, well, the sigma xy which implements this stress difference in the coordinate system aligned with that beam structure in the middle, x prime, y prime, and you see that there is something to be measured. So when implementing a stress sensor with the orientation of that of those 4 branches of the Wheatstone bridge, we have a chance to measure something. And now what we have to do is, of course, to to choose the material. So now it depends on which coordinate system is the chip actually in the crystal oriented with, and that is indicated here. So as usually, the chip coordinates of the edges are 1, 1, 0 directions. So this is actually like a 1, 0, 0 direction, and this is a 0, 1, 0 direction. And so these are crystallographic directions, and they need to be or the sensors implemented here need to be sensitive for longitudinal stress in that diagonal direction. And therefore, they need to be N elements, because N sensors have high stress response when aligned with the crystal coordinate system for the longitudinal stresses. And that is, that is how this is built. Does it say something about N doped here? Not yet. Yeah, here we see N doped Wheatstone bridge. So my guess, if it had been a guess, would have been right. But this was now logically deduced, as you should also be able to logically deduce this. And therefore, the material subjacent to the N-doped Wheatstone bridge, or embedding the Wheatstone bridge, must be a P material. This must be a P well or a P substrate of the CMOS process that was used here. And it was coming from us CMOS process. So this was done in this 0.45 micron CMOS technology at Micronas. Then it was just Micronas. Now they're called now TDK Micronas. And he did FE simulation, sensor modeling. He designed different sensor variants to find out whether his models had any realistic behavior also. And so he could optimize. He varied well the trench dimensions in length, in width, the thickness of the silicon chip, the size of the glass, and also the glass material. So there were 2 different glasses. One called Borofloat 33, I think from Monsanto, and then a glass from Schott, SD2. Schott is well known for glasses that don't react to temperature. You can have some Schott vessels to put into the stove, and it will survive the high temperatures without exploding or breaking, because it has very little thermal sensitivity. So the idea was to have something that has little sensitivity to temperature, because there is also the thermal bimorph effect in this sensor. So that would be a cross sensitivity. And so Mark tried out that SD2, but it turned out to severely reduce the sensitivity of the dimension of the sensor. And then you see that this is a sensor that only has this discrete sensor element, and then some contact pads to do all kinds of measurements in situ to characterize the structure. It doesn't have any circuitry on it. But it has quite some features that are actually characteristic of a CMOS process. So you see the Wheatstone bridge here with its 4 contacts. You see, well, the diffusion quite nicely. You also see some other contact here that connects the well and embedding the Wheatstone bridge. And then there are structures like dummy patterns that are supposed to, well, fulfill the design rules. And actually, Mark found out the hard way that actually it's not such a good idea to have these dummy structures, because they're made of metal. It's done for the lithography, so that the lithography comes out right, and of the other metal structures. And but metal is a plastic material, and when you expose metal patterns to 2000 bar, actually 600. He only had a setup up to 600 bar. It just deforms plastically, partly. This is very high pressure for metal lines. And so having something plastically deformed near the sensor meant that the offset of the sensor was also changed. There was a residual stress that changed with the number of cycles that were applied. And then as a function of temperature, higher temperatures, it was worse. And so he learned that actually one should better remove those dummy patterns. Yeah. And so you see these trenches. Yeah. These trenches are produced with standard micromachining techniques. Yeah. Silicon etching techniques. You know how to do that. You put the thing into a deep reactive ion etcher with a mask that is thick enough to protect the surface of the CMOS structures against 100 micron deep etch into silicon, a vertical etch. And this is this trench that goes down. And this trench going down then creates a silicon wall here on the side that allows this structure to, for instance, other color, for instance, to contract laterally if pulled longitudinally. Yeah? If there is a bending that changes, well, causes a longitudinal tensile stress, then this long structure acts a bit like a beam, yeah? And then it would like to contract like any beam does if you pull it along. Yeah? Of course, it's not a complete beam because it still rests at the bottom. Yeah? The silicon is bonded to the glass. So the bottom surface of that silicon structure here still rests on glass, just like all the silicon that you see around here. And here you see into the black hole, and where do you look at? At the glass. Now, why is it black? I don't know, some optical microscope effect. Yeah? You should see through, actually. Yeah? Or maybe there was some remainder of silicon still there. Yeah, then it's maybe just dark because you're looking into a black hole. Yeah, and but anyway, so this anisotropy we can see now with those arrows as well. And so one question was how to divide that space of glass and silicon into glass and silicon. Yeah? Should the glass be thin? Should it be halfway thin, or should it be thick? Yeah? And so this structure with a thin layer of silicon, let's think about this layer being very thin, yeah, bonded to the glass. Yeah? If it is very thin, it will not oppose any effective resistance against the contraction of the glass. Yeah? If the glass is forced to compress under an isotropic pressure, it will just pull the silicon along because of the little material that can counteract that. And then you essentially have an isotropic compression of that silicon layer from the sides. Yeah? Of course, the bottoms are pulling, yeah? But it's as if you were pushing on the lateral side, and it just contracts isotropically. Yeah? And well, apart from these slits, of course, then this compression, of course, will not be acting on those sides, but in the longitudinal direction. And so that gives you a response of a certain strength that is indicated here on this diagram, which is some sensitivity factor. And if you make the component really thick, the silicon component here is rather thick, glass is thinner, then the glass will compress, the silicon will compress less, but then the silicon is forced into a bending. Yeah? So it's the bottom of the silicon that is pulled towards the center, and the top has no such force. So what happens if you have a body of rubber and you compress it at the bottom? It will just bend. And so the silicon bends also, but that means that there is a tensile stress on the surface. It will be expanding. It will not be compressed like in the top right picture. It will now expand. And that means that the sensitivity to an isotropic pressure acting on that structure will be in the opposite direction. Because instead of a compression, the surface experiences an expansion. And so here's a sensitivity factor that has the opposite sign, minus 0.1. And if you go somewhere in between, you can be sure enough to obtain a zero response, because the contraction under the subjacent glass body and the bending due to the contraction of the glass body will just compensate. Effectively on the surface, nothing will then happen. And then you think you build your super duper sensor and it outputs zero as a function of pressure. Bad luck. Well, bad design actually. And so that's why these optimization studies are important. And so that's why ultimately this design was adopted with 100 micron of silicon on 1 millimeter or so of glass, because you can easily thin down silicon to the level of 100 micrometers. And then glass bodies of 1 cubic millimeter can be bought, or wafers can be bought and they can be diced easily. And so that's what ultimately Mark's choice was. Also, this has the highest sensitivity. That is the reason for the choice. Then, of course, many other aspects are studied in such a PhD thesis. Like, of course, now the linearity is a question. So if we go to 60 megapascal, 600 bar, is the sensor linear? And here's the pressure, and then the output voltage of the piezoresistive Wheatstone bridge. And you see that the response is very linear in all cases as a function of temperature. It varies because of the piezoresistive coefficient varying with temperature. Pi coefficient varies with temperature. You see that the higher the temperature, so this is cold, 40 degrees centigrade minus, and this is the last one, 125 degrees centigrade. Typical automotive specifications. Now that's not the temperature in the center of a motor where the pressure is being measured. It maybe indicates that the pressure will not be measured in the combustion chamber, but somewhere else where it is transmitted by another element onto that sensor. Don't expect this silicon glass component to be exposed to the combustion itself. But anyway, this is the temperature range that he studied, and well, you see that it's highly linear. Temperature range is also okay. Then he found out that this shot glass has a lower sensitivity than Borofloat. It has other mechanical properties than this softer Borofloat glass. You see the sensitivity here as a function of temperature. And you could also model that using COMSOL modeling. And so Borofloat is definitely the better material, although it likely shows a higher temperature cross sensitivity. And so this is also shown here. The SD2 glass, of course, shows you that, let's say, the output voltage in comparison with the output voltage is 25 degrees, varies much more moderately for the SD2 glass than for the Borofloat glass. So if temperature stability is a problem, is a concern, then SD2 may be the choice, or some other compensation technique will be necessary to compensate for the temperature sensitivity. And such methods exist, of course. And then, in this lower part, you see that he also did temperature cycling and found out that actually there is a drift. You see here responses back and forth, and you see how this varies. One glass in this direction, the other glass in the other direction, and so this was traced at that level back to the silicon layer, but the metal actually had a lot of problem. So when you see such drift, you always ask, what is it? Is it the bond between the glass and the silicon? Is it the glass maybe? There is it structures? And so we identified the silicon layer, I mean the silicon structure, not the silicon material, but not the silicon layer as opposed to the glass layer as the origin of that structure, because it happened in both glasses. And also how to package such a sensor. So here's a standard TO39 housing where the structure could be bonded to 4 contact pins, sitting on some flexible support. You do not want to bond the sensor onto the metal housing, because then you would prevent its contraction under the isotropic pressure. So elastically deformable material below, which is also a challenge, because elastically deformable materials under 2000 bars or even 600 bars deform a lot. So is this a reliable thing to let something be deformed strongly? And then the question of how to protect the sensor. Can you cap it with a standard TO5 cap with an opening and then fill it with some epoxy or elastomer to have at least the chemical contact with some jeopardizing substances removed? And so he did material studies here, taking common encapsulating materials like Sil-Gel and these 2-component epoxies, and StyCast is also an epoxy that is very common. And he tried to find out what worked nicely. So concerns of encapsulation is, first of all, the repeatability. Does the material support many cycles? Does it age? Does it delaminate from structures? And so, well, at least for the StyCast, he could see that, okay, there is a big hysteresis. So going up in pressure and down in pressure is not the same thing. So that's not a good example. And then for the other materials, it was kind of okay. But of course, I mean, that was just an initial study. That's not a product development. And so likely for a product development, many more such measurements under much more severe conditions, with more cycles and temperature variation and optimization of the curing conditions of the materials, processing conditions, in particular curing conditions of the materials in situ would be necessary. Okay, then after this nice example from our research with Micronas, let me show one example of a project with Intel. So Intel had this challenge of having, or still has this challenge of having these huge chips. I mean, CPU chips are 20 by 20 millimeters large, and there are many on a wafer. They're quite expensive because these wafers go through large numbers of process steps. So a wafer may be worth, well, tens of thousands of dollars in processing cost. And then you have a chip that still costs tens or hundreds of dollars. And you have to encapsulate it also. The silicon chip is worth nothing if it is not contacted to some ceramic substrate with fan out, with pins that it can connect to, so that it can connect to some electronics, peripheral electronics, to get data in and out, and to the screen, to the memory, to whatever. And so that's an interesting subject, because this interconnection of a chip to a substrate is not via 1 or 2 or 10 little contact pads. It's not wire bonding. There is not enough. There is not enough contacts. Along the periphery. Even if the chip is 20 millimeters large, and you put their bond wires all along the periphery, it's not enough. Yeah? They need to be everywhere. So people do flip chip bonding, with solder ball pumps on these bonding pads that are distributed over the entire surface. And then this structure is flip chip on a substrate that has the same arrangement. And these solder balls are then melted, undergo some metallurgical process between the materials of the substrate and the solder ball material, and some eutectic bonding. And then they cause a mechanical contact and, of course, the electrical contact at the same time between the two components. And the spacing between is then filled with underfill, and then some glob top material or some epoxy type polymeric material, carbon filled, whatever special material is molded around, and that's the chip that you buy and that you mount in your system. And that chip undergoes amazing temperature variations. I mean, my computer sometimes, yesterday afternoon, I could hardly type because it was so hot. For whatever reason, I didn't know. Maybe somebody hacked my computer and wanted to do something on my computer. And really was hot, looking for extraterrestrial planets or something. Yeah, it was amazing. Yeah, and so it goes up and down, yeah. And these composite materials, I mean, up and down means bimorph up, bimorph down, bimorph around, stress up, stress down. Cyclic stress is the worst thing for any combination of materials. Yeah? Shear stress will ultimately cause fracture by some delamination, by some fracture running critically full. So Intel wanted to know about the stress in these packages. Yeah? So how do you do that? How do you look into a package to get the stress value on? Well, our idea was to build stress sensors on chips that looked like CPU chips, but or similar chips, but were only designed to measure stress. Yeah? So we can measure what a real chip would experience under similar mechanical conditions. Yeah? And Benjamin Lemke, PhD student of mine, who's now with Endres and Hauser in Berlin, designed several variants of chips. I think I'm showing two here, filled with stress sensors. So really, the most complicated stress sensor systems that have been elaborated in my lab and maybe anywhere, because I haven't seen so many systems with thousands of stress sensors on the same chip. Yeah? And so this one is still moderate. Yeah? In size, it is 8 millimeter by 3 millimeter roughly in size. It's larger than any chip we had done before. It's as large as we could make them in the stepping technology of XFAB. We would have loved to have 20 by 20, but that was just not realizable. And then the system contains 700 contact pads, for this flip chip bumping. You don't see them here, but on a later picture, I think we see them roughly. So all the copperish structures, those are the locations where these flip chip bonding pads are located. So positions where on a real chip, the interconnections between the substrate and the chip would be performed. So this is kind of the arrangement that mimics the arrangement on the real chip. And below that, underneath, because these contact pads are, of course, on the surface of the CMOS. This is the last metal layer with an opening to enable a solder ball to be bumped onto it. And so below those structures, we arrange these sensor arrays. So there's a number of structures. So you see, for instance, 19 contact pads that were really used. So among those 700 contact pads, only 19 were used for operating the system. Whereas in a real chip, all 700 would be doing something useful to get information in and out from the system. And then it also had some ESD protection structures so that we could bond them without destroying the system components. Okay? There were 11 digital select lines, 6 analog signal, and then VDD and ground as additional important electronic, of course, potential levels. The 11 digital select signals were used for addressing individual sensors, so saying, okay, switch on the contact so that sensor out there on the left upper corner can be read out, and then switch the current from so to yeah. And so this is with 11 digital select lines. Yeah, you can address 2 to the 11 different objects. Yeah, essentially. Yeah, that is 2048 objects. And how many sensors were there? Well, 1244 stress sensors. There were also temperature sensors, and then, of course, the digital logic that translates the 11 input lines into what sensor is then used out there, and then this ESD protection. Yeah? So this is the general structure. That's the digital logic, the 11-bit multiplexer for finding the different sensors, and to read out all sensors, it took about 20 seconds. So that's not a high frequency system. Yeah? So you basically measure a stress state statically, and if you apply another force, you can again measure that stress state statically, and if the temperature increases or goes down, then don't do it too fast to be able to read out the different stress states. And so now we need to look at some structures in detail. So what were these designed for? So you see here structures that look similar. Yeah, all those you see same structures all over the place. Yeah, at many positions. So first of all, what do we see? We see some of those arranged. So let's say these two vertical rectangles and this more square structure. You find it here in the left corner, here in the middle. You know, always with a little bit different arrangements. But anyway, you find the elements. For instance, here in the middle of the chip, in the corner of the chip, in the middle of the long side, in the middle of the short side, and then also somewhere, well, the middle, well, between of that. So that is not a full map, of course. Yeah, it just picks out some critical positions. Yeah, and you can imagine that if we know what happens in the left corner, and the chip system is kind of symmetrically built, then we also know what is in the left and the right corner, or in upper left, or in the upper right corner. Yeah? That's why we only had to look for one corner. Yeah? Of course, there is only one middle, but it wouldn't be useful to have the same arrangement also up here, because what happens here is the same as what happens here. Yeah? That was our thinking. Yeah? And so by mirroring, reflecting these structures, you get a fairly complete picture of the stress distribution. Okay? And so what stress are we measuring? So there are these two elements that are measuring, well, sigma xx minus sigma yy in one of those structures, and then sigma xy in the other structure. In the form of an array of 7 by 7 such sensors. So that when a bump that nominally has that size, and after reflowing it is even a bit larger, then this will exert, because of the metallurgy, it will cause some stress. And then if there is shear stress, or whatever stress caused by that metallurgical process, we can measure that. And both these in-plane stress informations are extracted from these two structures. And then the third one in the middle, that's shown here, only has 5 by 5 because it has more contacts, and it's designed to extract the vertical resistance. So that's the best we can do to to measure the vertical force. This is the sigma index. Capital sigma is the stress combination that tells us something, at least in combination with other stress components, about the vertical stress. And there are some of those also. Yeah. And then we have the sensor chip 2, which consists of even more sensors, 1667, that are now regularly placed. So we have these fields, and each of these fields is filled with an array of, well, a two-dimensional array of the same piezo FET sensors, 32 by 16 sensors. Yeah. And then vertical resistance sensors also there, vertical normal stress sensors. And then we also have vertical shear stress sensors. So those are placed here. And then there is, again, temperature sensor, logic, ESD protection. And then more contacts to read out this larger number of sensors. And so again, the idea here was to not have, let's say, chip 2A only with piezo FETs, and then chip 2B only with vertical normal stress, and then so on for the other components, but to have them all on the same chip, but at least on a quadrant, so that we can mirror and extrapolate the global stress distribution on those chips. Yeah. And so yeah, these chips are kind of the most complicated CMOS sensor structures that were done in my lab so far. And yeah, company was quite happy with the results. They were able to determine where they have their critical positions in the chip. You know, I cannot tell you the details, yeah, because this is also proprietary. Our knowledge was the development of the systems, of the sensors, the invention of this vertical normal stress sensor, the shear stress sensor. That was our intellectual property. But the results about, you know, where Intel's chips fail, I'm not allowed to tell. Yeah, but it was not, let's say, super amazing. Yeah, it was just quantitative. Yeah, I mean, if I tell you that things start to delaminate more from the edges or from the corners, probably you will say, yeah, that makes sense. You know, it doesn't delaminate from the middle, yeah, where everything is glued well together and so on. So it's maybe where when two components contract differently, yeah, of course the shear stress is largest out there, not in the middle. So that is as much as I can tell. No? But anyway, they could then determine, you know, how thin the chip should be, because we did that on different chips, and how it depends on the chip thickness and the solder ball height and things like that. Okay, now after this, I would like to discuss one sensor in more detail, namely the pressure sensor, the standard pressure sensors. Silicon pressure sensors, yeah, of this classical design with a silicon membrane that deforms under a pressure difference, and which has been, let's say, one of the main early products of Bosch in the area of microsystems engineering. So what do you see here? You see again a cap, a TO substrate can with a feed through where pressure can be applied from one side, and then it has these electrical feed throughs for electrically contacting the structure. And on the other side, you'll see that these pins end up at locations where a bonding wire can be pulled onto a chip, a sensor chip that you see here with the sensor membrane in the middle. Sorry. And surrounded by, by circuitry. Yeah. And also this sensor sits again on a glass substrate. Yeah. Now it really sits firmly on this glass substrate. It is bonded anolically to this glass substrate, which is then bonded by some probably metallurgical, some eutectic process with some additional materials on this glass body, on this metal body. Metal has a huge thermal expansion coefficient in comparison with silicon. Silicon is about a factor of 10 smaller than normal metals. 10 to the minus 5 per Kelvin is the strain dependence, is the thermal expansion coefficient of metal. 10 to the minus 6 is that of silicon. So you cannot just fix a silicon chip onto the metal, because then you will have this thermal sensor instead of a pressure sensor. So you need to decouple the silicon chip from the metal, and that is done with a glass that has the same thermal expansion coefficient as the silicon. And in order for the boundary conditions of the bonding to the metal no longer to be felt at the level of the silicon chip, the glass body needs to be large enough. So now down there, the metal can do what it wants. Above, there is silicon glass material with the same thermal expansion coefficient. They don't see it. So that's the idea of this construction. And of course, the glass has also a hole in it that allows the pressure that comes through this metal tube to go through the glass to reach the bottom of that silicon membrane. So let's look at this in some variant, and then we'll look at the chip and the detail and the working in detail. So what do we have here? We have this silicon chip now in an alternative packaging, a naive packaging with directly bonded on some substrate, and then some feed-throughs through this package, and then some silicone gel filling it. That would be a cheap variant of the sensor, for commodity goods, where maybe the pressure information does not need to be so precise, and reliability is not an issue, and maybe hysteresis doesn't worry us so much. This protection by this elastomer that transmits the pressure to the membrane, silicon membrane, can also be done with parylene. Parylene can be deposited conformally, and it is an excellent protecting material against some environments. Other combinations that one sees is maybe ceramic substrates, where the substrate is itself has a thermal expansion coefficient similar to that of silicon. And then instead of just having this silicone protection, one also encapsulates it with a membrane, a tight membrane, a leak-proof membrane, or whatever harsh medium can be applied. And that harsh medium will only deform this thin membrane and transmit the pressure through this elastic material onto the membrane of the silicon pressure. And then there have been more complicated constructions with silicon interposer chips and so on. So let's look at the chip itself. Okay, this is, I got one sample from Bosch many years ago, which I photographed here, and then of course I put it under the microscope to see what is there. I did some reverse engineering, as we say. Now reverse engineering was allowed in this case because it's not the latest development. You can show everything about it. So this is authorized. And then what we see, for instance, here, I saw these structures. These are logos of Bosch. This is the logo of Bosch, and this is copyright of Bosch. And obviously in this area, their Metal One structures were were put, and they had metal 2 available as a second layer. They could design something which did not disturb the circuitry, this free space in this metal 2 free space, and then you have a, and actually this kind of things you find on many chips. Yeah, it's an there is a large number of original designs that can be found on commercial chips. The designer says, okay, I want to become immortal. Well, relatively, for a few years. Immortal for a few years. That sounds good. Yeah, and I put my favorite dragon or my favorite, I don't know what, Simpsons logo or something, you know, but just like Garfield, you know, splashing into the lasagna or something. Yeah, so that's an example of that. Yeah, and you see, of course, all around a lot of circuitry, analog and digital components. And then you see the central piece of membrane. So this is the size of the membrane. And then there is open landscape around the membrane to get away, get these thermally active and these metals that do all kinds of things thermally away from the silicon support of the membrane. So in cross section, this is all thick silicon up here, all around. This is the really thin silicon, a few micrometers of silicon for the deformable membrane that will deform under the pressure. And then there is the transition region where underneath, of course, there will be this anisotropically etched these walls, and then I don't know, maybe some additional safety space. These chips were indeed etched by KOH etching, or some isotropic, anisotropic silicon etching. I don't know if it's KOH, but very likely because that was the most common way of doing it. Here you have another variant that they also gave me with the same chip, now on a more on a cheaper package, in plastic, and then but there is still a support that somehow decouples the chips from the pressure below. Yeah. So now I'm looking at actually some elements, namely the stress sensors itself, namely here and here. Yeah. So we're looking now here at these two elements. Yeah. So on the left, along the left edge of the membrane, what do we see? We see a piezoresistive element that is connected out there to metal. We don't want the metal to be on the silicon membrane because then the thermal stress of the metal, the bimorph effect of the metal would influence the measurement of the membrane because it would help deform the membrane. We don't want that. So this is all silicon here, but we have it in different diffusions. So this is so we have, now let me think about again polarity. This is a 1-1-0 direction. So for sure this is 1-1-0, and then well, an equivalent, let's say 1-1-0 direction in this direction, so parallel to the chip, parallel to the flat of the wafer, and consistent with the edge walls of the KOH etching. And these piezoresistors are now parallel to these 1-1-0 directions. So they will be loaded longitudinally and transversely, and you can be sure enough now that they need to be P doped. Must be P material. N, we have a low piezoresistive coefficient, so this is P. So the membrane will be N material, into which the P resistors are diffused. So my guess here, my reverse engineering guess, is that this is highly doped P plus material, and here we have just P. And here we have P plus. So P plus, highly doped, good conducting material. And then we have some elements, some resistive elements. Of course, all these are resistive elements, but because of the high doping, these have low resistance. Then comes a high resistive, low resistive, and again a high resistive. Now, two parallel high resistive elements in parallel with the edge of the chip. Now, I can imagine that the membrane is deformed under a pressure difference. Let's say the pressure acts from my side of the whiteboard and pushes the membrane on the right down. Yeah, that will imply a stress, a tensile stress in this direction, because the membrane deflects with a curvature downward on the right. Yeah? So the membrane expands on the surface, so there will be a tensile stress acting on those resistors. That is going to be a transverse stress. Yeah? In this direction, we have the clamping of the membrane. It is attached to the silicon substrate there. Yeah? So it cannot expand. It cannot do the lateral contraction thing. So its strain is zero. And that means that there will be also some mechanical stress in this longitudinal direction. But that longitudinal stress is going to be only nu Poisson's ratio times this perpendicular stress perpendicular to the edge of the membrane. And nu for this 100 direction is actually quite low. It's 0.07. So this stress here is really small. It's 7% of the stress that we have in this sigma xx direction. We call that x. Now, there is this second element at the bottom of the chip. And let's look at that. Yeah, it is similar in construction. Yeah, it has these two p elements. I see the contrast is not so strong on your side, so let me write it in a different font. Yeah, so p. Yeah, whereas this is again p plus and p plus, p plus. Well, anything here is p plus. No, sorry, this one, not this one. And then those P pluses are contacted to metal, and then of course that has even lower resistance. And the main contribution of the resistance comes, of course, again from these low resistive segments here. High resistive segments, just like here. But now in the second arrangement, of course, the same membrane is now under this same pressure acting into the whiteboard, is deflecting into a curvature that goes down when you look up. Yeah? So there is a stretching, an elongation in this vertical direction. So what I drew blue here along that edge in this direction needs to be here now in this direction. The same blue arrow goes in this direction. And then the little, well, almost negligible stress parallel to the edge needs to be going here. So we see that this resistor here is stretched a lot in the transverse direction. And this resistor is stretched a lot in the longitudinal direction. And they are connected to each other. So if I go back here, sure enough, I can draw a resistor here, and I connect it to this resistor. And then there is another element sitting here opposite, which is of the same type as this one, parallel to the edge. And then here is a fourth element that is analogous to the one at the bottom. These makes four resistors that can be connected into a Wheatstone bridge. And pairwise, they have the same response, but the two pairs have different responses. And that is what we need for a Wheatstone bridge. So this is shown here, this schematic. I could now label those sensors with 1, no, let me do this now in blue. 1, 2, 3, and 4. So these are the sensitive elements, the piezoresistors. And here we see essentially 1, yeah, but of course 3 is of the same type. And here we see 2, but of course 4 is again of the same type. And here we label them with 1, okay, 2, 3, 4. Now the other way around. Should have looked at that slide closely before to name the resistors better. Yeah, so let me go back to here. Yeah, this is number 4, and this is number 2. Yeah, and 3 is correct. Yeah, and here we have 1 and 3, and 2 and 4. That is also correct. It's just the orientation that changed. Yeah, so 1, 2, 3, 4. And so, for instance, under a given pressure, it may be that 1 and 3 experience a change of resistance, whereas the other resistors experience another resistor and resistance change. And here I just wrote this down in very general terms. I said, okay, we have 4 resistors. They start with some value R1, R2, R3, R4, and then some delta R1, delta R2, delta R3, delta R4 are added. And then I said, okay, that's too general. Let's put those resistors to nominally the same starting value R0, all 4. And that's a good assumption because those high resistive structures are designed the same way. Yeah, I'm sure that the same cell was taken, repeated 4 times. Yeah? So that one has the same resistance, R0. And then there are resistance changes, which are now called delta R1, delta R2 with lowercase delta, that now for the sake of generality are left to be individually different. Yeah? And now when you do an analysis of the Wheatstone bridge, and calculate the offset that is measured between this contact and that contact, well, between those 2 locations here, with a voltage measurement device, then the relative change of that offset, V offset divided by the input voltage, is easily calculated as delta R1 minus plus delta R3 minus delta R2 minus delta R4. So those 2 resistors of the same type come in with the same sign, and the other 2 resistors with, with the other response come in with the other sign. And then so that's the first order analysis. That's quite easy to perform, and I think I'll add a little exercise so that you can just do a Taylor expansion of the response in terms of the small parameters. And then if you want to absolutely go to the next level of complication, you can also do the quadratic term, the second order term of the Taylor expansion. And it also turns out to be a fairly simple structure with delta squared divided by R0. So that also allows you to estimate the importance of including such a term. So if the resistance changes by, under your pressure changes by 10%, which would be a huge change, 10%. That means that delta R divided by R0 is 10%. So this divided by this is 10%. Then the changes of the next order of complication or of the analysis would be to the square. It's no longer 10%, it's 1%. It's 10 times smaller. So you make an error of relatively 10% with respect to the linear response. And then you want to think, is it worth going through the complications? Do I need a sensor that takes into account these nonlinear effects, or can I neglect that? Can I take this into account by calibration, for instance? What is cheaper? Do I need to build it into the system compensate for that, or can I do that after? Yeah. So usually people stop at this level here. Yeah. And that's fairly good because 10% resistance changes a lot. Yeah? If I had said 1%, then the second term down here would be 10 to the minus 4. Yeah? It's 100th of the 1% response that we get in the first order. Yeah? And then you could think, is that still nonlinear? And sensors that are linear to within 1%, are usually called linear. Yeah? Okay, so in this case, of course, if it was, so for the calibration, of course, it's much easier to have a linear sensor, and again, it's much better to drive these sensors under V biasing, to applying a voltage rather than applying a controlled current, because we have this ratio of resistances, and then the change of the resistivity with temperature is kind of compensated in this ratio. And the only thing that remains is actually the temperature coefficient of the piezo resistance. Yeah? That is not compensated in any scheme. That needs to be compensated differently. Yeah? So now here's again a slide that is filled with symbols, so it needs to be explained. Yeah. But maybe with the arrows I pointed at or I drew before, it will become more easy. So we have these resistors 1, 3, and 2, and 4. Yeah. Now I see that I should rework these slides. Now the orientation of the sensor is not what they are on the Bosch slide, but we have these two pairs of resistors. Ones are perpendicular to the edge, and two are parallel to the edge. Yeah? And we call a coordinate system here 1 prime, 2 prime, or x prime, y prime, or 1 on O, 1 minus 1 O. Yeah? And that just indicates, the primes indicate that this is not the crystal coordinate system, but rotated by 45 degrees. Yeah? So all the primes are implemented on the slide to avoid any confusion. And then we can think about how much resistor 1 changes relative to its nominal value. Yeah? And that will be the same as the fate experienced by resistor 3. Yeah? Because they are in symmetrical positions. So what happens to resistor 1? It's elongated under pressure. Well, resistor 3 will also be elongated just by symmetry. Okay? And that resistance is going to be, well, the stress at the position R1 or R3. The stresses are going to be the same here, again, for symmetry reasons. So the stress in the x prime direction, that is this component of longitudinal stress at this position here, multiplied by the piezoresistive coefficient that says how much this relative resistance change is, namely the coefficient pi x prime, x prime, x prime, x prime. Because in this resistor, the current flows in the x prime direction. The electrical measurement is done, of course, as a resistance measurement in the same x prime direction, and the stress is x prime, x prime. That is the stress x prime at this location. And then there is, of course, as I said, there is this little stress sigma y prime at this position R1 or R3. I should also write here my location. And that stress sigma y prime at that location is multiplied with the pi coefficient pi x prime, y prime, as written. And now I can, of course, make these notations a bit more compact. This stress here, I call it sigma transverse because it is transverse to the membrane edge. Yeah? So the T means transverse to edge. And then I have also this the stress sigma yy, which I call sigma longitudinal, yeah, to edge. It's not longitudinal to the resistor; it's longitudinal to the edge. Okay, I could also have called it parallel, yeah, to the edge. That's what it means. And the piezoresistive coefficients are usually also termed in a shorter notation. It's pi 1 prime 1 prime. This is the longitudinal piezoresistive coefficient for a resistor. I could also have called it pi longitudinal for that direction, which I call now the longitudinal direction. I could have called this coefficient pi 1 prime 2 prime, also the transverse pi coefficient for that transverse direction. That's a bit confusing, but you have to think it through once. To go back to the original slides and then see what is longitudinal. What do I, in terms of piezoresistive coefficient, what do I call longitudinal and transverse? It refers to the orientation of the resistor. And now I have stresses that I could have called also stress Oliver and stress Jonathan. That would have been okay. But then what does it mean? So maybe I should have called it perpendicular and parallel with two P's. No, that would not work either. So we always have this problem with the labeling. So here, T and L have different meanings. Once they refer to the resistor and once they refer to the edge. Now, what about resistors R2 and R4? Well, those relative resistance changes are also caused by a stress in sigma x direction at that location, and I'm drawing it in here as small arrows because it's parallel to the edge. This is a small stress, whereas the large stress acting on this resistor 4 is this one at this location. So the sigma x prime stress at the location 4, or equivalently 2, is this little stress, and it is multiplied by pi xxxx prime at that location. So this object here, well, no, let me first say what the sigma y prime does. The sigma y prime at that location is this large arrow. It is multiplied with pi perpendicular, x, y, y. And now let's call these piezoresistive coefficients by what they are named usually, namely pi 1 prime and pi 1 prime 2 prime. And what are the stresses? Well, this stress here at this location is the same. So that's the x stress. It's the same numerical value as the y stress at the location 1, 3. So the y stress at the location 1, 3, underline it here. Those are the same stresses. This is the stress parallel to the edge, or longitudinal to the edge. That's why I say pi longitudinal here instead of pi transverse is up here. So those are not the same. Different. And the stress in the y direction here at this location is the same as the x stress at this location. So this stress here we call the y. I was talking about the y. This y normal stress in y direction, is what we called sigma transverse up here. It's the same as the sigma xx up here. So this is how these two responses come about, and you see that the two resistor pairs have different relative resistance changes because the piezoresistive coefficients are multiplied, well, with switched stresses in both cases because of this 90-degree rotation. And so now you can insert these relative resistance changes. Of course, R1, R3, R2, R4 can be replaced by R0, R0, and then of course all those can be called delta R1 and delta R3 to be inserted in this expression here for the relative offset, the output signal of the sensor, and this relative output signal delta V output divided by input voltage after inserting well, this expression and that expression for the two types of resistors turns out to be pi 1 prime 1 prime minus pi 1 prime 2 prime over 2 multiplied by sigma L minus sigma T. So a very compact expression. That is the result of this substitution here. Yeah? So sigma L minus sigma T is the factor to which delta V over VB is proportional. And that is the difference between the thick arrows minus the thin arrows. And they are not the same. I mean, the longitudinal stress, sigma L here, and here is sigma transverse. Sigma L is about Poisson's ratio times sigma tau. So there is a factor. This is only 0.07 of sigma transverse, and so it's almost as large as sigma transverse with a minus sign. And the rest of the Wheatstone bridge, this plus minus here up here, just produces this this combination of pi coefficients as a prefactor in front, with a factor of 2 remaining. And then we have also the nonlinear term, which here as a, well, for the sake of completeness, I also inserted to find out that, okay, actually the squares of the stresses, the difference of the squares of the stresses are important. And then here the difference of the squares of these piezo resistive coefficient actually. So that was made more for you know, trying out. And again, well, essentially the sigma transverse remains, especially if you square the small part, there's almost nothing left here. So this is the dominant part. And here it is in the square with some piezoresistive coefficients that are also different from 0. And now we can also express these pi coefficients in this non-crystallographic coordinate system in terms of the usual pi coefficients referring to the crystal coordinate system, and pi 1 prime 1 prime is equal to this expression. That's obtained by this transformation rule of piezoresistive coefficients that you also have at the beginning of the chapter. And pi 1 prime 2 prime, well, is given by this expression. So we insert that, and then this prefactor actually simplifies to something even simpler, pi 4 divided by. And pi 4, so that is the piezoresistive coefficient that we want to have large in the crystal coordinate system. Which one is that? That's the one of P silicon. Okay, that's why I said we need P silicon in the first place. And then the end membrane needs to be the membrane needs to be endowed so you can produce some P resistor membrane. That pi coefficient is something like 138 times 10 to the minus 11 per Pascal. It's a substantial coefficient. And here we have the product of two coefficients, so the large one and then this small thing. So it's not that you know, this is kind of from the same size as this object to the squared. It's even much smaller. So the nonlinear response is suppressed by the fact that these pi coefficients of P silicon are quite low. But the conclusion that we need pi resistors is, of course, unambiguous. Now, we haven't a pressure sensor. We have a stress sensor that somehow responds to the deformation of the membrane. And so, of course, sigma L and sigma T will depend on pressure. Both of these stresses at the locations of the resistors will be depending on pressure. And then also, it will depend on where the resistors sit. Yeah? Do we have to put them here in the middle of the edges? Or should we put them in the corners? Or more to the middle? Yeah? These are design questions that we need to answer also in designing a sensor. Sure enough, Bosch chose the right position. Yeah? And we need to see why. Yeah? We are doing reverse engineering. So what we need is actually a model of the membrane. Yeah. But before that, let me just summarize a few consequences here. So in these traditional silicon pressure sensors that are still, sold by the millions, yeah, for all kinds of measurement purposes, those have these anisotropically edged edges along 1,1,0 directions, and then sigma L is much smaller than sigma T because of Poisson's ratio. And then we need pi 4,4 to be large, and therefore we take P resistors, because pi 4,4 is larger than in N material. P silicon will be much better than N silicon for those resistors. And if we have stresses of about 10 megapascal, then we also know that the signal will be about 1% relative of the input voltage. And then the nonlinear part will be 1% of the 1% roughly. The temperature resistance, temperature dependence due to the resistivity is compensated by the bridge design if the bridge is operated in the voltage biasing mode. And while that due to the pi coefficients remains, that could be minimized by having highly doped piezoresistors. Highly doped piezoresistors are less sensitive to temperature, but then you lose piezoresistance because they are also less sensitive. So it's a matter of, again, trade-off. What do you like? Do you have a calm part, but not such a high performance sensor, or do you want to have a high performance sensor? And then you need to invest something for compensating the temperature. But what now essentially we're lacking essentially is sigma L and sigma T, and their dependence on the pressure P pushing on the membrane. So we need a membrane model. And well, there have been some models in the literature elaborated by people like Mark Allen, who's now a professor at University of Pennsylvania, one of the top Ivy League universities in the US, in Philadelphia, beautiful campus with old buildings and the Ivy ranking going up the walls. I was there once for a 2-week sabbatical, short sabbatical. It's very stylish to be at these Ivy League universities. I like it. Somehow you breathe in this erudition. I don't know if that is an English word. Gelehrsamkeit. Every brick, breathes out some knowledge, wisdom. Anyway, so here you have a cross section across a membrane under a pressure difference. And of course, what we would like to know is how it deforms, and more particularly, what that deformation means in terms of stress at the surface over the area of the membrane. So these models have been elaborated already in the 90s. And so here is a summary of some of the elements. So it is easiest to represent the pressure needed to produce some central deflection of such a membrane in this term. Rather than W as a function of P, it's easier to represent P as a function of W, because that's a relatively simple function. it's a linear function plus a cubic term. Yeah? When you solve that for W, to express W as a function of P, you have to solve a cubic equation, and that is more complicated. Yeah, so that's why people have represented that always in this term. But you see that actually there are these two terms, yeah, the linear and the nonlinear term. And if the nonlinear term were negligible, then it would be easy to turn around the equation because you have P proportional to W. Yeah? So what are the elements that go in here? Well, it's first of all the height of the membrane, or the thickness of the membrane, if you wish. The size of the membrane, the edge length, the elastic modulus of the material divided by 1 minus nu square, Poisson's ratio and elastic modulus, and then the deflection divided by, again, the thickness with some parameter in front. And the cubic term is similar, it just has W over AH cubed times another coefficient B. And these coefficients A and B, they're kind of tricky. They take into account many effects. So there is some buckling behavior that is described by this. So if the membrane material has a pre-strain epsilon 0, which is pre-stress divided by elastic modulus, pre-strain. So imagine this is pre-strain compressively by 1%, and this would be minus 1%. And this can be multiplied by A over H square. And then there is a critical stress that determines of whether the membrane is buckled or not. And this critical stress, again, is a function of Poisson's ratio and some numerical constant, which people like Mark Allen and others in those times determined by numerical simulations. And then the coefficient B is even more complex. It has also all kinds of dependencies on Poisson's ratio and then also on this pre-strain. So these are kind of fit functions. This is nothing fundamental, physically fundamental. It's the best model that could somehow have a decent simplicity model, but that take into account all the variations that are there, namely dimensional variations and material variations. And then there are, again, coefficients C1, C3, 1, 3, 2, and 3, 3 that are tabulated here, which are fitted to the data. So with this, you can predict the pressure needed to deflect a membrane in this nonlinear regime. And of course, inversely, you can then solve this numerically to extract the deflection caused by a pressure. And so here are some, some calculated responses where you have the deflection as a function of pressure. So this is kind of the inversion. Deflection as a function of pressure, or if you imagine this this curve to be read the other way, pressure as a function of W. You can make this horizontal axis the ordinate, and this is the abscissa. Then you read pressure as a function of W, the same thing as you have here as a model, pressure as a function of W. And this is, you see that this is a linear curve plus some cubic contribution that adds to this linear component. Here the same. So this is how you can project the formula into this graph. But here it's represented the other way around. What deflection do we get as a function of pressure? And you see that for thick membranes, first of all, the deflection is much smaller. Of course, it's stiffer, cannot be deflected, and it's much more linear as a function of pressure. So if you would like to have a linear sensor, a mechanically linear sensor as a function of pressure up to 100,000 Pascal, 1 bar, then 10 is certainly better than 4 or 2. where you have mechanical nonlinearities. And where do these nonlinearities come from? Why does this deflection of a membrane under pressure not just continue like that, but somehow become slower and slower? It gets harder and harder to deflect more because it bulges out of the plane, and then its length changes. It gets under some in-plane pre-strain, which would like to, or pre-stress would like to bring it back to the central position. And the stronger it is deflected, the harder this pre-stress or this in-plane stress would like to pull it back. Yeah. So you're not only working against the bending. The bending alone, the bending stiffness alone makes this linear response. But the fact that you have at the same time an elongation stress that develops the stronger you are deflecting, that contributes to cubic power. And then, so this is shown here, and then here I just drew how linear the response is, how W divided by the linear part of the deflection is, and then for the thicker ones, we see that this ratio is 1, for 10 and 8 micron thick. For 6, it already becomes 90% at 1 bar. So 6 micron is 10% wrong in deflection under 1 bar for silicon material. So, well, silicon 150 gigapascal is quite representative of silicon, and Poisson's ratio is something, well, which is also reasonable. And we're assuming no pre-stress of the membrane and a typical membrane dimension of 0.5 millimeter. So I see that my time is over. And what I will do next time, Monday, I will just finish that chapter first, and then we'll discuss, because there are 6 or 7 slides left, and those are not super complicated. And then we'll do the homework. We'll have a homework orgy Monday and Tuesday, probably. Sounds quite joyful, yes. And so I will submit another series of exercises on which you can also work until next Monday and Tuesday, and I'll let you, submit them until Monday morning, 6 o'clock. Then Matthias also had time overnight to work on the problems, and then I'll see you Monday afternoon. Okay, bye-bye.